We're going to talk about whole number multiplication in real-world scenarios. You're going to use your knowledge of how to visually represent multiplication problems to both solve and set up new word problems. These are such important teacher skills to have. So what we're going to do is help develop your ability to help students decide what expression matches a word problem. So when they say, how do I solve this? And also to be able to create scenarios. So if you're talking about multiplication, when would you ever see that in the real world? We'll be looking at 4 different contexts: repeated addition, multiplicative comparison, ordered pair, and area and array. So let's go ahead and get started here. Our first problem is repeated addition. It says Jack walked his dog 2 miles per day for 3 days. How many total miles did Jack walk? Well, I can draw a picture for this, and if I think about it, if I'm drawing out the scenario, I can say, well, Jack walked 2 miles, and then the next day he walked 2 miles, and then the next day he walked 2 miles again. So each of 3 days, 2 miles per day. When I look at this picture, it's a linear model of multiplication, and I have 3 sets of 2. 3 sets, 3 groups with 2 in each group. The 3 are the days, and the 2 are miles per day. In a word problem, the per day tells you the group size. So we can translate that right into multiplication. All right, let's write a problem now. So this last one was linear, so let's do this one as a discrete set instead. Write a repeated addition word problem solved by 4 times 3. So 4 is going to be our groups, and 3 is going to be our group size. So we're going to have 4 groups with 3 items in each group. So I can think in the real world what this might be. Well, this might look like shopping bags with something in them. What can I put in my shopping bags? Maybe books. So let's have 4 sets of 3 books. So 4 times 3 might become 4 trips to the store, and I bought 3 books per trip, and then I can turn that into a story problem. So let's see. Every time Ben goes to the comic book store, he buys 3 books. If he goes to the comic book store 4 times, how many books does he buy? On to our next one. Let's do a multiplicative comparison. We're going to be comparing quantities. Phineas has 4 times as many stickers as Ferb. If Ferb has 9 stickers, how many stickers does Phineas have? Well, when I'm comparing, the bar models work really well. So 4 times as many, I want to draw one bar that is 4 times as long as a second bar. This is going to be Phineas's, this is going to be Ferb's, and the story says we have 9 stickers, so if one box represents 9 stickers, then we have to put a 9 in each box, and I can see this is 4 groups of 9. So this is 4 times 9. 4 sets of 9 stickers. All right, let's write a problem. So here a multiplicative comparison solved by 3 times 2. So again, I'm going to go with my bar model, and I say, well, how many times? And if I were to read this out loud, 3 times, 3 times. So I need a bar model that's 3 times as long as the second one. Then I can think about, well, let's compare something that's 3 times as long or 3 times as much. I'm going to go with Scooby-Doo, and I'm going to say that Velma and Fred are studying. So knowing what I know about them, I think Velma probably studied more, and Fred probably studied less. So 3 times what? 3 groups of 2. That's my 3 groups of 2. So since I have 2 in each box, Fred will get 2 as well. And so then I can set up my word problem just by describing my picture. Velma studies 3 times as long as Fred. If Fred studies 2 hours, how long does Velma study? All right, let's move on to the next one. This one sounds completely different, the ordered pair Cartesian product. 2 students are running for class president, Amy and Bob. 4 students are running for class treasurer, Claire, Dave, Emily, and Frank. How many combinations of president and treasurer are there? So these combination problems, my instinct is to list out the combinations. And as a math teacher, I know that a tree diagram is a powerful tool for doing combinations. So I'm going to have a president and a treasurer. And the president is either Amy or Bob. And then I'll have 4 options for a treasurer. It's either going to be Claire, Dave, Emily, or Frank. Claire, Dave, Emily, or Frank. And so this is going to be, I can look at this picture. It looks like multiplication. 2 sets of 4. 2 groups of 4. 2 times 4 gives me all of the combos. I could list them out if I wanted to, Amy and Claire, Amy and Dave, and so on. But my picture tells me I'll have 2 sets of 4. Let's write one. So if we're going to do one of these combination problems, 3 times 2 ordered pair, I start by drawing my tree diagram. 3 sets with 2 branches each. And then I think about, what could I do here? A lot of times food combinations like ice cream and toppings, or wardrobe combinations, pants and tops. I'm going to go with marbles, and I'm going to describe qualities of marbles. So 3 qualities a marble could have. I'm going to say it could have a color of either green, red, or white. And then I'm going to say, marbles come in large and small. So there's my tree diagram, 3 sets of 2, ordered pair. I could list them out again if I wanted to, but instead I'm just going to write my story. Sam has a bag of marbles. The marbles are either green, red, or white. Each color comes in either large or small. How many different types of marbles could Sam have in his bag? All right, moving along to the next one. Area or array. These ones are usually pretty straightforward. My secret garden is a rectangle. So I'm going to draw a rectangle that measures 2 meters by 3 meters. What's the area of my secret garden? Well, here's my 2 meters, and here's my 3 meters. And if I extend my measurement into area from linear into 2D, I can see I have 2 sets of 3 or 3 sets of 2. This picture can be interpreted either ways with my area model. All right, and then finally, let's write one of these, and we'll do array this time. So instead of tiling with, like square meters or something, I'm going to think about, like cans on a shelf are often arranged in rows and columns. So I'll be thinking about rows and columns that aren't tiles here. So let's think, Girl Scout cookies. So Girl Scout cookies, when you buy them, those boxes are sectioned off. And so let's say that I'm going to have 3 sections. And if you get the good cookies, sometimes they're big and fat, with 2 cookies per section. So yeah, Girl Scout cookie boxes seem to be getting smaller and smaller though. So here I'm going to have 3 sections of my cookie box, and they have 1, 2 cookies each. I have an array of 3 by 2. So my word problem might be a box of Girl Scout cookies has 3 sections that each hold 2 cookies. How many cookies can the box hold? So there's my 1 cookie, 2 cookie, 1 cookie, 2 cookie. I'm circling them because they actually kind of look like 3 by 3 with rectangles, but I'm making my cookies, 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 cookies. This problem might have been even better with bigger numbers, like 5 times 4 if I'm doing cookies. But anyway, you can see the idea with rows and columns with the array problems. That's all for this video.